Yep.
You know, we have another nice long weekend.
That would be kind of cool, but I can't do it. All right. So we are still kind of talking about the Linux file system. We'll probably still be doing that for another week or so, depending on the pace. So we'll go ahead and open up some tabs here. Okay, so that's one. And for the most part, we are actually only relying on one of the links here. Let me see which one it is. Nope, that's a user perspective. Let's see, where is it? There we go. Once we get into the homework assignment, the link is from the homework assignment itself. All right. So we're still kind of talking about the superblock. The superblock is the very first thing you have to do because that's the only thing you can find when you are talking about an extension to file system. So let's go back and go to the superblock. The superblock is always located at byte offset 1024, which means there's another 1024 bytes before the superblock that is not used at the beginning of the file, from the beginning of the file, block device, or partition formatted with extension 2. What that means is if you have already partitioned your hard drive, then you can use the partition device itself, like SDA1, the one with a number on it, in order to access extension 2 or the superblock. I think last time I created a particular one, I actually mounted it, created some files in it. So now we can use that one for illustration purposes. And I'm trying to think of a good, easy way to do it. So let's find out whether this will work or not. So I'm going to use a ln-s to create a symbolic link to the folder from last time, which is 0215. Oh, no, it doesn't have, oh, the extension 2 of test 1 is over there. So, and I have to give a name for this particular folder. Let's call it the same thing. Okay, so when I ls, you can see there's a file called extension2 test1.bin here. Yep.
When you were doing the ln command, you were able to browse what was inside check what was inside the folder. How did you do that when you were?
I use tab, which is a shortcut. I mean, auto completion key.
Yeah.
Yep.
And then, so you got it over to MBR Viewer, and then how were you able to just look inside that?
Tab.
Tab again.
Yep. Yeah. If you type a part of a file name and you press tab, it will auto-complete as much as it can. If you have two files that share the beginning of the same file, that share the same beginning part of the file name, it will complete all the way up to that point, but no further. But when you press tab again, it will list the files that begin with that portion of the file name. It's a pretty handy feature. I think it's faster than using the GUI to find a file once you know how to do it. Okay, so what I have just done, this is also a very useful feature in a Unix type file system, is I have just created a symbolic link, which in a way is kind of like a shortcut in Windows, but this is actually a better way to do shortcuts. Shortcuts are not really that complicated. I mean, shortcuts are really just regular files, where the GUI or the Windows environment, will interpret it. This one is actually a little bit better than that. There's also something called a hard link. A hard link is something that I cannot easily explain until I have explained what inodes are. In this case, you can look at this as a shortcut. So that way I can refer to the same file from multiple places. And also, if I do a hex dump on this one, it will actually do a hex dump on the original file. So if I do this, this is actually a hex dump of the original file.
So
now yep, go ahead.
I'm sorry, what was the command to create this symbolic link?
It's the ln-s command.
Got it.
So this is the command that I used to create a symbolic link. Symbolic links are very, very useful in many different situations. even when you have to specify like names of your source files and so on and so forth, it can come in pretty handy. All right, so we are now looking into, yep.
But aren't you going to have issues if you try to tar that so we can download it?
You can make tar follow symbolic links. Okay, let's go that way too. So when you say man tar, oops, follow symlinks.
That's cool.
So that way, you know, if I have a symbolic link to a file that is not in the actual folder, it will actually go grab that file, and the tar version will have the actual file instead of a symlink to that file. It depends on what you're doing. You know, if you're tarring the entire structure, then you don't need to use, you know, the dereference. But if I'm tarring this, you know, so that you guys can have access to the files that we work on today, then yes, you know, following the symbolic link will be useful. Okay, good question. All right, so we are looking at a hex dump of the superblock at this point. 400 in hexadecimal is 1024. So this is the beginning of the entire superblock. The other 1024 bytes before the superblock is not used. Okay. So now let's switch back here, and I'll just kind of briefly go over, you know, some of these you know, numbers here, and we'll also refer to the homework assignment. So in the homework assignment, we are now done all the way up to here. Okay, last time we were locating the magic number. Let's go ahead and locate the magic number again in the hex dump, just so that we know what to do. You know, just a refresher, because it has been a week since last week already. The magic number is here. In decimal, the offset is 56. 56 in decimal is 38 in hexadecimal, because it is 3 times 16, which is 48, plus 8. Okay. So if you want to do a base 10 to base 16 conversion, you know, divide it by 16 first, that will give you, you know, assuming the number is within 255, the first number will give you the quotient will give you the most significant nibble, and then the remainder will give you the least significant nibble. So one will be a hex digit on the right-hand side, left-hand side, and the other one will be on the right-hand side. So now we have to go to 438. So 430 is here, 438 and 439 are here. Okay, those are the 2 bytes. Do they match what we're expecting? Well, let's take a look. 16-bit value identifying the file system as extension 2. It is fixed to extension 2 supermagic of value EF53, and this is using the little endian interpretation. The little endian interpretation means the least significant byte is stored first. In this case, the least significant byte is the 53, so this one should have a lower address, or it will be the first byte in the superblock. If I switch back to the hex dump, that's exactly the case, because we can see the 53 is the first byte, and then the EF is the second byte. So the signature is found. Are we doing okay with this so far? Okay. Next, let's go back to the homework assignment and see what we have to do next. Figure out the block size and the block group size. Now this part is kind of interesting because the first thing I want you to print once you confirm that the superblock is good because the signature is good is to tell me how big is a block size. A block size has to be at least 1024 bytes, but it can also be a lot bigger than that. So I want you to print it out in decimal without the 0x prefix. It means it's a decimal number. And if you look into the documentation, okay, let's go back to the documentation here. If you look at the block size, this is block count, that's log block size. This is how we get to the block size. But remember, this is not the size itself, it is the log of the block size itself. That's actually not accurate either. Let's look at the definition of log block size and see what it means. It gives you this equation. The block size is computed using this 32-bit value as the number of bits to shift left the value 11024. Okay, So that means whatever number is in S log block size, you have to use it as the number of times you have to left shift 1024. What does that mean? How many people know what, at least, what is a shift operation in C? Yes? Okay. Now what does that do? What does left shift do to a number, to the value of the number?
It increases it
It multiplies it by
power 2.
by 2. Okay, so if I shift twice, what is that doing?
Multiply by 4.
Multiply by 4. Very good. So that means, n is log block size. The actual block size is basically 1024, which is the base, times 2 to the power of n. That's the number. But to the power of something, there's no need to use the power function, which is a floating point subroutine, and it doesn't really get you really good results. So the way to do it is to say 1024 left shift by n times. That will give you the number that you need as a block size. Are there any questions about this? Because left shifting n times is to multiply by 2 to the power of n. It's the same thing. Okay, just a quick quiz here. What if that n is 0?
Then it's 1024.
Then it's exactly 1024 bytes. What if that n is 3?
Then it's 6 kilobytes.
It's 8
Oh,
kilobytes,
yeah, sorry.
because it's 2 to the power of 3, which is 8. All right. So now that we know this, let's see if we can find that. So this is at offset 24, and itself is a 4-byte number. In other words, we can potentially specify a huge block size, because if you specify 16, which doesn't seem to be a pretty big number, what is the block size when this number is 16? It's not 64K, it's 64,000 bytes, or there-ish, because you have 64K times 1024, which is a pretty big number, and that's one single block. Let's go back to our dump here and find out, whether, what is the block size for this particular file system. It's at offset 24 in decimal, which is 18 in hexadecimal. Did you guys know how I did the conversion?
Divide by 16.
Divide by 16, you have 1 as a quotient, so the 1 becomes the most significant nibble, and then the remainder is 8, and that becomes the least significant nibble. Okay, so we have to look into offset 18 in the dump, so it becomes 418. In this case, these 4 bytes represents our log block size. It seems to be a pretty darn big number, right? I mean, it's 2 followed by,
It's little endian.
6 zeros, but it's little endian, so this really is just 2. Okay, so that means our block size is what?
2 kilobytes.
4,096 bytes, because it's 1024
Right.
times 2 to the power of 2 in this case.
I gotta get that power 2 thing down.
Okay. Okay, so I'm just going to write some notes here. So in our test case, the block size is 4,096 bytes. Okay. So we got one part of the assignment done here. And then the next thing we want to do is to find out what is a block group. How many blocks do we have in a block group? Okay, so we have to look into here. And number of blocks per group is here at offset 32, which is 20 in hexadecimal. So we go back into the dump, go to location 420, and this is the number that we are looking at. So how many blocks do we have per group here? This number is basically 8000 as a hexadecimal number. So that's about 32,000. Okay, it's 2 to the power of 15. So I will just write that down too. The number of blocks per group is 2 to the power of 15, which is approximately, okay, Perl people can tell me, this is not a real operator, so I'm just gonna do this, approximately 32,000. This is not an operator in any language that I know of. This is, and so is this. Do you guys know what this would do in C?
I know it does something, but I don't remember what.
We'll do a decrement first and then.
No, that's a tilde symbol.
No, that's a tilde.
Oh, tilde symbol means it doesn't work in C, but it does. This is a Perl operator. How many people program in Perl? Nobody.
That's after Python. Python's next, then Perl.
Python is very different from Perl in many, many ways. The philosophy of Python is completely opposite of that of Perl.
If I know C and C++, should I go Perl or Python? Should I learn Perl or Python next if I've done C and C++?
In terms of the syntax, Perl would be closer to C and C++, but in terms of the cleanliness of the language, Python is probably a little bit cleaner. All right, so we got those two particular numbers figured out. So do we have any questions about this portion of the homework assignment? Try to figure out the block size and the block group size. Questions? No questions? Okay. So the next thing to do is to load the block descriptor table. The block descriptor table is right after the superblock, but it is block aligned. Okay. Okay. So right here, let's stop and see. But what do we mean by it is after the superblock, but it is block aligned? All right. Picture may be helpful in this case. So I'm going to use a spreadsheet, because a spreadsheet is a big table. It's already pre-formatted. Makes it easier. Don't need to remember that. All right. So here, let's say, okay, this is the key. Each row is a 1024 byte. Okay, each row is represents 1024 bytes. Okay, that's the key. And we'll go ahead and mark the beginning of the entire partition using a horizontal line on top of this row here. So we just mark the entire row, go to Format Cells, go to Borders, and mark the upper line here. And we can make it even a little bit thicker. Oops, that's not the thickness. It's the second one. There we go. And we can even be more fancy and change the color. There we go. All right. So that marks the beginning of the entire partition. What is this part here?
Empty.
Not used, right? And what about this part here? That's our super block. Now, in this particular example, we have a block size of how many bytes again? 4 kilobytes. Okay, 4,096 bytes. So if I were to find the what's the name of that block descriptor table, where am I going to find it? Tell me the row number. It will be row 7. The row number is this number. I'm using the row number of the spreadsheet, not the offset from the beginning.
Can't see it from here.
Sorry.
But the super block is one block, correct?
The super block is only one block. The super block is only 1024 bytes long. Okay, so okay, all right, so let's go back to this description here. The block descriptor table is after the super block, not before, but it is blocked aligned. So that means, you have to take this entire block. This is one unit, this is one block, because our block size is 4,096 bytes. Okay, so that means the next available block starts here. Is that okay?
Even though that first 1024 is not used, it's part of the first block.
Neither are these 2,048 bytes are also not used. Yep.
So if our block size was 1024, then it would be starting at row 5.
That is correct.
Okay.
Yep, and that can happen. It depends on how you format your extension to file system. You can specify a 1024 byte block if you want to. Okay, so here comes another question. It's not related to this discussion, but it is, just in general. why do you want to control the size of a block? You know, what does it buy you when you have a smaller block size, and what does it buy you when you have a larger block size? And what is the optimal block size, by the way?
Well, if you can't have a file bigger than the block size, right?
No, a block size is just it's just the smallest quantum, you know, that the file system can allocate. In other words, if I were to create an empty file, okay, or a file of 1 byte, let's say I have a file of 1 byte. In this particular system, since one block size is 4096 bytes, the system will have to allocate 4096 bytes, even though my file only has a single byte in it.
Okay.
Yep, Sean, go ahead. I thought you had a question. No? Okay. So why do I want to use a smaller block size sometimes, and why do I want to use a larger block size other times?
Well, if you use a smaller block size and you have a large number of small files, you're going to end up using a lot less space overall.
Right.
On the other hand, if you need to be able to address your blocks in in however many bits you're using for, I think it's in your inode table.
Mm-hmm.
And so, if you have a 2 terabyte drive and you have 1 kilobyte blocks, you're going to need a pretty big inode table to be able to hold that. And I don't know exactly what it uses, but the bottom line is if you have a 32-bit in, you need to be able to you need to be able to address all your blocks in that number, so that's your limited number of blocks.
Right.
So the smaller the block size, the more overhead you have?
Exactly. The more overhead that you have, when you have large files. But when you have tiny little files, everywhere, then the overhead, which is the other overhead, there are 2 types of overhead. One overhead has to do with whenever you allocate a block, how much of it is actually used. That's one overhead, or the portion that is not used is wasted, and that's your overhead.
Okay.
If you have a 16K block size, and most of your files are only a few hundred bytes, then you're wasting a lot of space.
Right.
Okay, but that's only one part of the equation. The other part of the equation is all these blocks. You can still create huge files using a 1 kilobyte block. It's just that your file is chopped up into a lot of these tiny little blocks. And the system needs some kind of index to basically say this file consists of 4,000 of these 1K blocks. So your overhead becomes more expensive in that case when you have a small block size, because your index structure to index all the blocks of a particular file, that becomes expensive.
And every block has an inode, right?
No, that's not the case. An inode can point to many different blocks already, but you still have to increase the number of indexes. Because each block needs to have its quote-unquote own pointer pointing to it.
That makes sense.
So so when you have a small block size, you end up with a lot more pointers, and that takes up more space.
Okay.
Practically speaking, unless you're dealing with extremely large files, the block size really has very little impact on the theoretical upper limit of a file size.
Okay.
And we'll get to that part later too. But I just want to kind of move that topic forward, in case you guys want to think, well, why would I want to control the block size, or why is that even a variable? Why can't the system just kind of fix one and be done with it? And the reason is there's no one single size that is optimal. It depends on what kind of file you're storing. Okay, if you're storing a lot of video clips and big files like that, then a larger block size would make sense. Because if your file is each one is 1 gigabyte large, then a 16 kilobyte block is not bad. I mean, because you will have a lot of those blocks. Only the last one will have a little bit of waste. Is no big deal.
Right.
It also depends on your hard drive. The newer hard drives have a sector size of 4 kilobytes. So making your block size any smaller than 4 kilobytes is not good for performance, because now you can have blocks all over your place. Okay, think about this. Let's say I have a block size of 4 kilobytes and the hard drive sector size is 4 kilobytes. So they match up exactly. When I need to read 4 kilobytes in the file, it only has to go to one sector and read the entire sector, and it's done. Now think of a file system formatted to 1024 byte, 1 kilobyte block size. Now those blocks, I still need 4 blocks to represent 4096 bytes, right? But no one says those 4 blocks has to be right next to each other. They can be on 4 physically different sectors. So now your hard drive has to go to all 4 different sectors, and for each one it will read back 4,000 bytes, of which only 1024 bytes are actually used. So from that perspective, it is very slow because your latency time is bumped up a lot in that case. All right, so that's the consideration that we are those are the things you have to think of when you want to determine the block size of your file system. Okay, so now we load the block descriptor table. Okay, we just found the block descriptor table. In this table, read the first block descriptor entry of the table. It contains the block number of the inode table of block group 0. Okay, let's find out what that means. So we want to keep the super block around because it is still useful. So we'll open a new tab for that. And now we are into the block group descriptor table. Okay, this is the block. It's actually block group descriptor, not block descriptor table. I should probably fix that just so that the terminology is consistent. Fixed. Okay, so in our other slide, we will take a look at the block group descriptor table and the structure of that. This is the block group descriptor table. It is an array of block group descriptors. Each one to describe parameters of a single block group. It provides the location of inode bitmap in the inode table, blah, 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 blah. Okay, so we'll go ahead and look at each entry and then find out what exactly do they do. Let me switch back to this portion here. I'll keep this part here, and I'll use another terminal to take a look at our block group descriptor table. So we'll have another hex dump -c, and it is called extension to test1.bin. Which offset should I be looking for now?
4096.
4096 in decimal, and in hexadecimal that would be 1000. Okay. So we are going to shift to here. This is the beginning of our block group descriptor table. Okay, so let's highlight this portion here, and then we'll read the notes a little bit more, or read the documentation of extension 2 a little bit more. What is one block group descriptor? One block group descriptor has how many bytes? This is the offset. This is the size. All you have to do is to look at the last entry. The last entry is at offset 20, but it has a size of 12, and it is reserved, which means it is not being used by extension 2. So that means each item or each entry is how big? 32 bytes. Okay. So that means if I switch back to my hex dump here, 32 bytes will take up exactly 2 rows because each row represents 16 bytes. This is one entry. In fact, we only have one entry because one block group is already big enough for the entire file system in this case. We have a tiny file system, so one block group is already big enough. So now we want to look at these 32 bytes and find out, okay, but what does that mean?
How do you know that you only have one?
Sorry?
How do you know that there's only one entry?
Because everything else are zeros.
But there's nothing that's telling us how many entries there should be.
There is one in the super block. It will give you the number of block counts. And since we already know the number of blocks per block group, and we know the number of blocks, we know how many block groups we actually need. Okay, let's go back here and take a look at the blocks count here first. Okay, so we'll go back to, I think, this window here, and this is the beginning of the super block. And according to this is an offset 4, it's a 4-byte number. Okay, so from here we'll be looking at this portion here. How many blocks do we have in the entire file system? This is the number of blocks of the entire file system. It's 400 in hexadecimal. This is the least significant byte. This is the second least significant byte. These are the most significant bytes, which are just leading zeros. So if you look at these two numbers, it is 0400, and that's 4 times.
I think it's 1024.
It's 1024. So the entire file system only has 1024 blocks, but each block group has 32,000, can handle up to 32,000 blocks. So that means, one block group is much more than what we need in this particular small file system. Is that okay? So you can actually back compute the number of block groups you need by the total number of blocks in the system and just divide it by the number of blocks per block group. All right, so let's go back to here. Okay, so let's see, open a new tab. Okay, so for the block group descriptor table, it has all these entries: block, bitmap, inode bitmap, inode table, free block count, free blocks count, free inodes count, and so on and so forth. Let's take a look at the first one, the block bitmap. 32-bit block ID of the first block of the block bitmap of the group represented. That's basically an address. It's an address to find the first block in this particular block group for the bitmap of this particular block group, of this particular block, excuse me. And then the second one is also a 32-bit block ID. Whenever you see block ID, it's kind of an address, but it is counting in number of blocks. Okay. And by the way, what is the block size of our example? 4096 bytes. So whatever this number is, how do you get to the actual offset in the file system?
Multiplied by 4096.
Multiply that by 4096, which is actually pretty easy in hexadecimal, because 4096 in hexadecimal is 1000. So when you have a number here, you just have to shift it by enough zeros, 3 zeros in hexadecimal to get to the actual offset. I'll talk about that. Okay. Let's go back to the homework assignment, because you don't really have to access every single thing here. Okay, so we just loaded the block group descriptor table. Well, we haven't really loaded it, but we were looking at it using hexdump. So we want to load inode table of block group 0. Okay, and how do we do that? We make use of the inode table here. 32-bit block ID of the first block of the inode table of the group represented. Are we doing okay so far? We have to use the inode table, which is a pointer. It is really a pointer, except it is not a byte addressable pointer. It is a block addressable pointer. And if we take a step back, the inode table is from offset 8 of a block group descriptor. So we have to look at offset 8 from the dump. So offset 8 of the dump is this one here. Are we doing okay so far? Okay, let me just repeat this part again. These 32 bytes is one block group descriptor. And inside here, from byte offset 8 to byte offset 11, these 4 bytes according to the documentation, is our inode table. It tells me how to find the inode table. It is only 4, but we have to remember to multiply this 4 by 4096 in decimal or 1000 in hexadecimal. So now where do I find that block?
4000.
Yep, 4 and then followed by 3 zeros, which is here. So this is the beginning of my inode table. Are we doing okay so far?
So okay, would you explain why that's 32 bits again, the block group, the descriptor table?
Yes. It's because a block group descriptor structure, each record is like this. If you look at the offset to the last element, which is just reserved, which means it's not used, it has a length of 12 bytes. So that's why I know each item is only 32 bytes.
Got it.
Okay. Yep.
You're going to.
Do you want to go back to the dump?
Well, so the inode, I'm back to the inode, so the
inode table. Mm-hmm.
So you go back and I see where you found that, and it's the 0400, which is little Indians you block around.
Mm-hmm.
Okay, but I guess is that an actual address you're dealing with? I thought somehow it was an offset of some sort.
It's an address, but it's expressed in number of blocks. Okay. The only thing of an extension to file system that does not depend on the block size is which one?
So block size is
The super block itself. Okay, the super block is the only block in the entire extension to file system that does not depend on the block size, because otherwise it becomes a chicken and egg problem. If you don't know the block size, you cannot find the super block, but you need to find the super block to know the block size. It doesn't work out, right? So that's why the super block is always at offset 1024, and itself is always 1024 bytes long.
Was the inode number actually 4 up there? Which portion are we looking at?
The 4 is this 4 here.
And it is literally 4.
It's literally, it's a 32-bit representing the value 4.
4, okay.
Yep.
And then because our block size is 1000 hex, 4 times 1000
In hex is 4000 hex. That's
okay,
right.
I'm with you. Thank you.
Yeah. So this is the beginning of the inode table of the first block group in the file system. Now in this case, we only have one single block group, because one block group can handle 32,000 blocks already, and that's more than what we need because we really only had 1024 blocks in the entire file system. Is that part okay? But in a larger file system, we can take a look at a much larger file system later on to see how many block groups it has, and then each block group has its own descriptor in that table. All right, so getting back to the homework assignment. Load the inode table of block group 0. Note that the inode table is in number of blocks, and we just figure out the block size from the previous section. Your program should use malloc to allocate storage needed to store the entire inode table. If you want to just read and just use a lot of seek operations, that's fine too. But I think it's better off. You're much better off just read the entire inode table because it's not really that big. Okay. How big is an inode table?
I was just going to ask that.
Okay. Now, if you think about it, who do you think or which data structure will tell you what is the size of each inode table in number of blocks, of course?
One number of blocks,
Yeah.
possibly the super block.
It will be in the super block, yes. So if we go all the way back to the discussion of the super block, it will tell you the number of inodes, and it should tell you the number of bytes per inode. Inode size is right here. Do you see this part here? So the inode size tells you the size of each. Oh wait, we don't want that one. We want the inode table. Okay, let's go back. inode table is used to keep track of every blah, 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 blah. Okay. There's one inode table per block group, and it can be located by the BG inode table in this. This is the BG stands for block group. Inode table associated with this. There are S inode per group inodes per table. Okay, the prefix is telling you, this is coming from
Superblock.
the superblock, because everything that has a S underscore as a prefix comes from the superblock. So that means we just have to look closer in the superblock to find the inodes per group. So I'll cheat.
It's number 11.
Number 11? Oh, underscore per. Okay. So this is a 32-bit value indicating the total number of inodes per group, which is also the number of entries of your inode table. Because you only have one inode table per block group, so that means the number of inodes per group is the exact number of inodes of entries per inside the inode table of a block group. Okay, I'll draw a picture later on that makes it a lot easier to understand. But first of all, let's go back to the dump here and find out what this number is. And this doesn't tell me the offset. I think the offset is discussed here. How come I cannot find it?
Do you want to look in the
Yep, right here. But how come my search doesn't find it, when I'm... Oh, because I have the underscore. It's inodes and then the underscore over here. This is at offset 40 in decimal. So in hexadecimal, this would be 28. Okay. So if we switch back to the hex dump and go to 428, this tells me the number of inodes per block group, which is also the number of entries per inode table. Whew. Okay, that's a mouthful. So how many do we have?
1024.
It's 1024. Very good. Okay, that turns out to be a pretty magical number. Okay, so we have 1024 inodes per block group, and as a result, we have 1024 entries in the inode table. Okay. But that tells you how much you have to read in when you're reading in the entire inode table. Okay. So I have to go find out where the inode table discussion is. I'm going to close the ones that I don't need anymore because it will just get kind of confusing. It's confusing me more than anyone else.
Oh no, I'm right there with you.
Okay, so we have the inode table here. The inode structure, in other words, each entry in the inode table has, has this particular structure. And how big is one inode structure?
128 bytes.
128 bytes. Are we starting to see a pattern here? It seems like all the quote-unquote record size are powers of 2. Okay? Because powers of 2 are very easy to handle. How do you multiply something by a power of 2?
Shifting.
Shifting, exactly. And that's why these entries all have, if it's not originally a power of 2, they will pad it to become a power of 2, because this way we can compute the offsets very convenient.
Just a second.
Yep.
You said that the inode table size was going to be 1024.
There are 1024 inode structures in the inode table.
That's how many inodes per
Oh,
group.
that's very different. Okay.
Yep. I'll give you a big summary later on, so that you guys will have a kind of mental picture of everything that we have talked about up to this point. Okay, so this is one inode structure, and inode structure has Okay, let's go back, take one step back and think about what an inode is. An inode structure really represents a file or an entry or something in the file system. So we are already down to at the point where we can identify actual things in the file system at this point. Each inode structure represents a thing, a file, a folder, a block device, in a /dev/something. Okay, and it has these entries. Some of these are fairly easy to understand. Size, okay, size is a 4-byte thing at an offset of 4, and if you look at size, it is just a 32-bit signed value, indicating the size of the file in bytes. In revision 1 and later revisions, and only for regular files, it represents the lower 32-bit of the file size. The upper 32-bit is located in another structure. Yep, another.
What happened to negative size?
I have no idea. But basically, it's broken up into 2 because nobody uses revision 0 anymore. So almost, we can find the revision also from the superblock. In other words, how can you tell whether you should use this interpretation or this interpretation? The answer is it's also in the superblock. The revision number is in the superblock. Okay. All right. So do we know where? Do we know what is the first entry in the superblock? I mean the inode. What is the first inode structure of the entire file system? We know this is the beginning of the inode table. We know that an inode table has how many bytes again?
128.
I mean it has 128 times the number of entries per inode table, which is 128 kilobytes in this case.
Okay.
Because there's 1 kilobyte, there are 1 kilo entries, and one entry has 128 bytes. So that's why we have to read in 128 kilobytes for the entire inode table. Is that making any sense?
I think so.
Okay, the inode table, I thought it started at 4,000 hex, no?
Yes, it does start at 4,000 hex. So it's down here.
Oh, there we are, okay.
Yep. So and each entry has 128 bytes. So how many rows are we looking at with 128? 128 divided by 16 is, come on.
8.
8. It's exactly 8. So that means all these entries belong to the same inode structure. Okay? Are we still okay with this?
That's not 8, is it?
It's not 8 because the rest are all zeros.
Oh, okay. Thank
So
you.
if they're all zeros, if it's a repeating pattern,
Thank you.
it just has an asterisk symbol
Got it.
to mean that they're all going to be the same as the previous row instead of
Sure.
listing all the rows here.
So that's one inode structure in our inode table.
Yes, that's one inode structure in the inode table. In fact, it is the first inode structure of the entire file system, which has a certain significance.
It's a super block.
No, it's not a superblock. It's well, let's go back and read the homework assignment. Okay, analyzing the root inode. Now we have located the root inode. Okay, the inode table is an array of inodes, or inode structures, I should say. The structure of each inode structure is described in the linked document at the beginning of the assignment. The inode structure corresponding to the root directory is the second entry, not the first. Okay, so in the dump here, I have just highlighted the first one. It's not the first one that is the root directory. It's actually the second one that is the root directory. So we are looking at 8 all the way up to here. This is the entry that we are actually interested in. Yep.
So what does the first one denote?
The root inode.
That's inode 0, right?
I don't know for sure. That's a good question. Okay, inode table. It's probably described down here. The first few entries of the inode tables are reserved. In revision 0, there are 11 entries reserved, while in revision 1 and later on, the number of reserved inode entries is specified in S_first IN of the superblock structure. Here's a listing of the known reserved entries. The first one is bad blocks inode.
Oh.
So that means, if your during the format operation, if you ask E2FS, E2FSCK can do it too, but when you format, when you say MK E2FS, you can actually make it scan for bad blocks, and it can mark the bad blocks and use the first entry to represent all those bad blocks.
So those bad blocks are actually files? They're represented as files?
No, each bad
everything's
block
a file?
is just a block.
Oh, okay.
Okay, we still haven't got to the concept of a quote unquote file yet. Okay, we are still talking about blocks and just very vague terms.
But I thought every inode pointed to something, and every something was a file.
Yes, except in this case it's not.
Okay.
The first entry does not.
Okay.
Does not point to that. Okay, the second one is a root directory inode. So that's the important one that we want to access. Are we still doing okay so far? Okay. All right. So the second one, which I have already, I just highlighted that a little bit earlier. I guess when I switch window, it loses the highlight. Yep.
Wait, but I thought it said that the values were like 1 through 6 on that table we were just looking at.
Right.
And if those values, I don't know what those values are, but if those values are the inode table numbers, and it looks like,
The indexes is off by 1.
yeah, that's what I'm wondering is, is value 1 really offset 0, or is there, or do we still not know what's stored there? Because there's clearly something there in our hex file.
Mm-hmm.
But I'm wondering if it's the bad inodes. Or
Well, we'll go ahead and interpret index 1 as our root directory, and then see if it makes sense, okay? Because that's one way to check for sure, okay? Because the next one is the ACL index inode, which is, which will give us, some completely different results, okay? So we'll just use the assumption that index 1, or the second entry in the table, is what we are looking for, okay? So we're looking at this one here, and the interpretation is based on these offsets here, okay? Are we still doing okay? All right. And this is supposed to be the root directory. Now, when you're looking at a root directory, the mode byte or the mode bytes, in this case, will give you a pretty good idea of whether we are looking at the right thing or not. So I'm going to right-click and open a new tab on just this one 16-bit entry. This one single 16-bit entry tells you a lot about what the file is, and it also tells you all kinds of permissions of this file. Now remember, each inode structure is basically representing an entry in the file system, for the most part, okay, except for the bad blocks and the ACL and stuff like that. So in this case, if I think this is representing the root directory, it should have the properties of the root directory. Look through this part here and tell me, which one is which bit has to be set if this were the actual root directory. It's, yep.
The directory bit?
The directory bit, very good. So the directory bit is here. This is the entry. It means if I take a look at the mode bytes, the first 2 bytes, as using the little endian way to interpret the 2 bytes, this is the bit mask I can apply to it. If I apply this bit mask, which means if I AND using the bitwise AND operation to AND those 2 bytes with 4000 in hexadecimal, it should be a non-zero if this were a real directory. Okay, are we still doing okay so far? So let's do a sanity check and see whether that really is the case for the entry that we are looking at or not. So we switch back to the dump, and it has lost its highlight again, but that's okay. Okay, so we are now looking at these 2 bytes as a 16-bit number. Is bit 4000 set? I don't even need to do a bit mask here, do I? Because this, as a 16-bit number, it is 41ED. S41ED is the bit 4000 set.
Yes.
All right, so it is a directory. So I'm fairly sure that this is the entry that we have to look at.
But you've got a 50-50 chance, right?
Yeah.
So,
Yeah.
I wouldn't be feeling that great.
But even if you look at E, if you look at ED, E also has the most. E also has the same bit set too. So even if you interpret it incorrectly, you will still see this as a directory,
You're okay.
which is bad. Yeah. All right. So, okay. So here's the next thing we have to do. So now that we have located the root inode structure, then we can see the first thing you want to do is to see whether it is a directory. So we just did. Okay, it is a directory. Otherwise, we can continue. We can proceed to list the content of the root directory. In other words, we're now getting into the file system now. Okay, we just got a hold on to the inode structure of the root directory, which is where everything starts. Okay, everything starts with the root directory. So now we want to look at, okay, what is the content of the root directory? The test file system that I have set up only has one folder set up. Okay, so it should be pretty simple. At this point, the program should analyze the I flags and see if bit extension to index.fl is set or cleared. If it is, print the following message: the root directory is indexed. Otherwise, print the root directory is linearly linked. Okay, so we want to look at I flags, I_flags. So we'll go back to here and look at I_flags, which is at offset 32. So open the new tab again. And we want to look at which one I cannot remember things. We want to look at index_fl. Index_fl is right here. Okay, so as a 32-bit number, I want to see if this particular bit, this is also bit 16. Okay. Does everybody understand how the nomenclature, how I number the bits? Each hexadecimal number is 4 bits. The first one, or the least significant digit in hexadecimal, represents bit 0 to bit 3, bit 4 to bit 7, bit 8 to bit 11, bit 12 to bit 15. So this is bit 16 to bit 16 plus 3, which is bit 19. Okay? And it is at offset what again? Offset 32. Okay, 32 in decimal is 20 in hexadecimal. So we can switch back to our dump again and look at 20. Well, we'll have to add 20 to it. This is the second entry. So we are looking at these 4. Yep, it's 32. So I flags is all zeros. So that means it is not indexed. Okay. All right. So in this particular test case, the root directory is not indexed, which means you have to print it is linearly linked. All right. So now that we know the root directory is linearly linked, it is time to load the root directory. From this point, it's a matter of tracking down the I block field and load the blocks into memory for an analysis. Okay, so let's go back to this portion here. And I blocks is at offset 28. And we'll go ahead and open a new tab here. I blocks is a 32-bit value representing the total number of blocks reserved to contain the data of this node. So this is the size, not the where we want to load it from. And where's the location? I block. Okay, there we go. Now this one is a little bit interesting. I block is itself an array. It's an array of 15 items. Now this is where things can go really, really kind of interesting. And and this is okay. Let me just read this part here, and then I'll give you a kind of more pictorial representation. I think the spreadsheet included, actually has a pictorial representation of this. I block. It's a 15 entry array. Each item is a 32-bit block number. Okay. All right. So if I were to use should I use the whiteboard? I'll just use my spreadsheet. Where's my spreadsheet? Here. I'll use sheet 2 to represent, the blocks part here. Okay. So this is I_block. How many entries do we have here? 15 entries, right? So we'll just go ahead and number, entry 0, 1, 2, 3, and extend it all the way down to 15. Oh, there are 15 entries, so there's only index up to 14. Okay. Each one is a 32-bit block number, but the row of the 32-bit block number is different depending on which entry we are looking at. The first 12 blocks are what we call direct blocks. Okay, so we'll go ahead and go to the spreadsheet and mark the first 12, which are these guys here. Okay, so I will just, okay, this is what I'll do. Direct blocks. And change the alignment to center, vertical, middle. Okay. What it means is, if you want to get to the first block of a file, that entry will bring you there. In other words, in this case, if you want to find the first 4096 bytes of a file, this will tell you, or this entry, whatever the value is, will tell you where to find the first 4096 bytes of that file. Okay? If you want to locate the next 4 kilobytes of this file, this entry will take you directly to that block. This entry will take you to the third 4 kilobyte blocks. So that means if your file only has 12 times 4 kilobytes, bytes in the file, you only need the direct blocks. This will tell you, so one look up here will get you the block number. You multiply the block number by the block size, and that's the offset on the hard drive you have to go in order to find that portion of a file. Are we doing okay so far with the direct blocks?
The block number
by the block size. Yep. Because everything from now on, they're block addressable. So every time you quote unquote address something, you're numbering the block, not the byte offset. Are we doing okay? Okay. Offset, the 13th entry is a little bit special. The 13th block of the file will be the first block ID contained in the indirect block. All right, so this one is special. The first 12 blocks, the 13th entry is the block number of the first indirect block. Okay, so we are reading this part here. So what does that mean? This one is called an indirect block. Okay, the indirect block. Okay, I need to kind of shrink it a little bit here. The indirect block points to obviously a block. The question is, what is the row of the block that this guy points to? It's an array of direct blocks. So, yeah, go ahead.
No, I'm just saying, oh my goodness.
Yep, go ahead.
So is block, can we assume that block, those first 12 blocks are linear, or they're in line? Or
Nope.
you have
Nope.
to
They
go
can
and
they can
chunk-
all go over they can go
chunk them
all over the
and
place.
go and pull them all together, kind of thing?
Well,
You wanted to load
you
up
just
the
have to
file?
find out which 4K block you want to access, and then you just look up the item of that particular entry, and then go to that block, and you're good to go. Okay, so even though these numbers can be all over the place, there's no need to look up again. You just have to go directly to that block, and that block is a portion of the file itself.
Yeah.
Okay, the indirect block points to another table. So we'll call this the There's a particular name to that too, so I just want to use the same terminology. Which is a block containing an array of block IDs containing the data. Okay. So this is okay. Okay, I think that's the best way I can describe it without being more confusing. Okay. So so there's a pointer here. Let me draw a pointer.
Are we saying that we're never going to get to this point, obviously?
Unless you have a lot of files in the
Yeah.
root directory.
Right.
Okay. So then each one of these will go to a data block. Okay, I think I have a better way to do this. I'm going to use color coding. Change the background color to a light yellow color. So everything that is in a light yellow color, it doesn't look light yellow on the screen here, but everything of that color is basically a pointer to a data block. In other words, that block is a part of the file. Okay. So the direct block itself does not point to a block of the file. It points to a block. In this case, this block has 4096 bytes, which contains how many 32-bit entries? 1024 entries. Okay. So that means, up to this point here, I can have, what is the maximum file size up to this point? If I have to use this entry, what is the maximum file size that I can handle?
48 kilobytes before that.
It'll be 12 times 4 kilobytes plus 1024 times 4 kilobytes too.
Oh, with that, I think went before that.
Oh, okay, including the indirect block. So what if that is not big enough? Because we're only talking about a 4 megabyte file at this point. No, it's not 4 megabytes. Yeah, it is. Okay, we're talking about approximately 4 megabyte file here. If you need a file that is bigger than 4 megabytes, what do? You use the indirect block here. So the question now is, what does that do? I think you guys know the answer already. The indirect block points to a
Another block, another I block.
It points to an indirect block, right?
well, it
Which
points
then
to. Okay, I'll just highlight this one, OEM. It points to a indirect block. So this block itself is indirect.
This means an array of indirect blocks.
Yes.
Wonderful.
Okay. So an indirect block, okay, I will highlight these two using the same color because they are both pointing to file block ID blocks. So I will highlight these two exactly the same way because they serve the same purpose. I'll use a light green color here. Okay.
That helps actually.
So that means each item from here points to a yellow block. Okay. So I'll just go ahead and I'll just use two, to represent that. Okay, so 1, 2.
Are these any particular size or?
Each block is 4096 bytes because that's a system-wide configuration. So this one goes here, this one goes here, and so on. So we have 1024 entries in the indirect block. Each indirect block points to a file block ID block. And then each entry in the file block ID block points to an actual data block in the file.
And that's the same as a direct block. A
No,
data block.
a
in
data
file.
block. A data block is not a direct block. A data block is actually a part of your file. Yep.
I have to ask, do you know what the advantage would be of doing this rather than simply having, say, the last space in the first indirect block array be, instead of, so in column D of the spreadsheet, why not just have that be either, you know, null, the null byte, or the null 2 bytes, or a, you know, the ID of the next indirect block, or the next direct block array, so kind of make it a linked list. I don't understand why they wouldn't.
Well, this method makes it so that, you know, for accessing little smaller files, it is extremely efficient because, you know, the direct blocks points to a data block in the file directly. So anything that is up to 12, in this case 12 times 4, which is 48 kilobytes, is easy to access. The first 48 kilobytes is like lightning fast to access. If you have anything that's greater than 48 kilobytes and up to about 4 megabytes, you only need one indirection. So, and then the next one up will handle, you know, a lot more than that. So the next one, you know, you guys can guess this one already, right? It's an indirect block. Okay? And what does it point to? Yes.
An array, is it an array of indirect blocks?
Yeah.
Yes, exactly. Yep.
So let's say we've gone through all of our direct blocks and we still need, you know, we still haven't gotten everything.
Then
We're
it moves
still
on
needing-
to.
Yeah, so now we're going towards indirect block. Is it true that in column D, the top row, like row 1 of column D, would be the address of the next block of data for my file?
That is
right?
correct. Yep.
Okay.
So in terms of your data, you know, the data blocks of your file, this is the first entry, second entry, third entry. This is the 12th entry.
Mhm.
This will be the 13th entry.
Mhm.
So you have the 13th entry, and there are 1024 entries in this block.
Oh.
Okay, so there are 1024 entries in this block, and there are 12 here. So that will make this one 1024 plus 12. That's what this one is pointing at. Okay. Yep.
As for a response to his question,
Mm-hmm.
if we wanted to get to a chunk at the end of the file, we'd have to traverse all the arrays.
If it were a linked list, but this
Yes.
solves that, so that's the.
This one
reason.
can get you direct access
Yeah.
to each item, at the most with only 3 indirection, even if you have a humongous file. So, yep, go ahead.
I'm still a little confused at the relationship between a direct block and actual data from your file. A direct block points to a block of data from your file?
A direct block points to, okay, each entry of a this portion is a 32-bit number, and it is the block number of a data block, which is a block that represents content of your file. Yes.
Okay. So a direct block is a pointer to content or a
A
file.
direct block pointer is the block number of a data block in the file.
Okay.
Yep. Okay, so are we kind of doing okay here? I'll just finish this little picture here and with a pointer pointing here to here, and then each entry from here will point to a blue block, and then each entry of a blue block will point to a yellow block, and each entry of the yellow block will point to an actual data block of your file. So we can we can probably imagine, you know, or calculate the maximum file size, you know, based on this structure here. It's pretty big. Okay, by the time you get to the 13th, you know, this item here, it's already pretty big. You know, you need a pretty big file to exhaust, you know, this entry to even move on to this entry. Okay, so we're running out of time today. It would be helpful if you just kind of watch this again and then start to code your program up to this point. Okay.
What about our practice quiz?
The practice quiz. Well, let's finish this first, you know, because we're kind of in a roll here, because this stuff really needs to be continuous. You know, missing one class, you know, kind of make it not so continuous anymore. So we'll probably finish, you know, the file system. Maybe we'll just, you know, have one fewer exam in this case.